Martinez de Dios, and I'm full professor at the University of Seville, working as head of the Perception and Autonomy unit of the GRBC Robotics Lab, which is coordinated by Aníbal Ollero, and also a member of the board of directors of Eurobotics, one of the largest and more reputed organizations in robotics in Europe, joining not only academia, but also industry with more than 300 members, 400 members, something like that, okay? So the title of my presentation today, okay, is Forest Fire Monitoring and Measurement with Multiple Cooperating Drones, okay? So first of all, I will briefly introduce the group in which I participate. So we are a large group of about 70 members in average. We are mainly devoted to unmanned aerial systems, okay? We have both vertical and horizontal capabilities to develop this technology. That means that we cover all the technologies involving from the design, aerodynamic design, mechanical design, up to intelligence in terms of control, planning, perception, autonomy, etc. Okay, we are running now 12 European projects. Okay. One of them is coordinated by us, okay, and we also have one ERC, European Research Council Advanced Grant, okay, which is Griffin, okay. We are although we are an academic group, we are part of the University of Seville. We have a strong practical environment. Of course, we join and we produce a number of publications, okay? But we don't stop on this, but we put all the systems into practice. We have several infrastructures, including a large indoor test bed in our lab. Also, we have outdoor test beds, okay, for flight arenas. And also we have, well, in total, we have 2 outdoor test beds, one in the School of Engineering itself, but now the School of Engineering is at the corridor of the airport, so we cannot fly. It is a nested environment of about 60 by 30 meters, something like that. This is our outdoor test bed. And also we have an outdoor test bed outside of the corridor in which we can fly freely without the need of a nest. And in this case, we have several thousand of square meters for the test beds, okay? And finally, once that we develop this, so first we test the technologies in the indoor test bed, which is about 20 by 10 meters, something like that. Is one of the largest in Europe as well. And then we go to the outdoor test bed, and finally we go to the final applications. Here in these images, you can find, for instance, a bridge and viaduct that we have been doing performance there, also tunnels. Yes, also power grids. Okay, we go to the final applications, and in many cases we go to the company. Okay, that means that we have now about 12 contracts with companies, so about 12 European projects in H2020 and Horizon Europe, about 10 national projects, okay, about 12 contracts with companies. Okay, now I'm going to show some brief descriptions of what we have done. Maybe the sound is, maybe I can mute it. Okay, I'm particularly proud of this. This is one system that we developed in the Eurobotics and the European Robotics Challenge, sorry, in which we were finalists, okay, out of more than 130 participants, okay. So in this case, what we develop is a system for light object delivery and logistics within a factory, okay. This is indoors, fully indoors. We had a fully autonomous GPS-denied navigation system, and we did it to deploy components that are needed by the workers, okay? In this case, it was experimented with TRL 7. TRL is a code that means technology readiness level. 7 means quite advanced. Okay. In fact, we tested that inside an Airbus company, and you cannot say Airbus, please stop the production because we're doing an experiment. Okay. So this was quite a successful for us, and I am proud because I was the coordinator of this. Okay, and for this we also got an award, which is the best drone application award in the year that we produced that. It was 2018, sorry. Okay. Yes, another thing is we develop, let's say we are leaders on international level at area manipulation. That means that a drone is endowed with robotic arms, of course, lightweight robotic arms, such as it has capabilities in order to do some kind of manipulation. So in this case, in this video, is the deployment of a sensor, okay? So the robot is absolutely autonomous. Everything is computed on board, okay? There's no participation from any man here. And we tested that in a cement factory, a real cement factory that is very near Seville. Well, it's about 100 kilometers from Seville. And in this case, the robot just builds the map, the 3D map, using the LiDAR, okay? And with that, we did that through a slump technique, okay? Once that the map has been generated, it is sent to the operator that decides the place where the robot will deploy the sensor. And then the robot does the planning, the navigation in a fully autonomous way and without GPS, because there are a lot of metallic components and structures, and there's no GPS, not good GPS reception here. And finally, the robot just goes to the final destination and just does the deploying in a fully autonomous way. That is another thing, that is the use of aerial robots for inspection, physical inspection of infrastructure. Here you can see that we developed one robot, also fully autonomous, that has the capability both of flying and also by using the ceiling effect, it can go to the lower part of the deck, move and deploy the sensors, okay? So in this case, here's the safety pilot. Of course, we need to have a safety pilot for regulation here, okay? But the drone is fully autonomous, including the takeoff, navigation, doing the experiment, motion, etc. In this case, we develop a GPS denied localization using information fusion, which is one of the main topic in my unit and in most of the projects in which we participate, okay? This is some results that we recently obtained also in another project that is coordinated by us. The call is Aerial Core. Okay, in this case, we develop a fully autonomous navigation system in order to map the electrical power lines. Here, in this case, this is a beyond line of sight flight of about 3.4 kilometers. Okay, this is some map that we obtained in the final demonstration of the project, and the objective here is to map all the surroundings, in particular the vegetation that is surrounding the electrical assets, the electrical power lines and the electrical towers, such a way that it's possible to measure the distance, okay, because for the regulation point of view, there is a minimum distance that should be done, okay, in order to ensure the safety of the power line and prevent fires and prevent cuts of electricity. So this is And this was done by a fully autonomous navigation. In this case, the navigation was using GPS, okay? And it has a LiDAR, a solid state LiDAR, in which it is capable of gathering information from the LiDAR and in real time using SLAM techniques, combining SLAM together with GPS information. It can accurately locate the robot and build the map, everything in real time and onboard the drone, okay? So our objective is to have everything in real time and everything on board, okay, which is the main objective in the robotics community. And finally, this is some videos that we got in another project, which is the Griffin Advanced Grant project, in which we are developing technologies for flapping wing robots. Okay, the challenge is not only to, let's say, to design the bird, to build it, but the main challenge is to make it autonomous. That means that it has to gather the sensor measurements, process them in real time, and being capable of using these estimations to guide the drone, control it, do the planning, etc. Okay, this is something that is unprecedented. Okay, nobody has done. I think that we have been the very first ones in the world that have done this, not to make a flapping wing robot, but to make it autonomous, or to provide him some autonomy. Here you can see a video in which the flapping wing robot is doing perching maneuvers. Okay, this is our indoor test bed. Okay, this was also the very first time in the world. Here you have a video. I'm going to move this because probably you cannot see it well. So in this case, we are using perception using an event camera. Event camera is another paradigm, different from typically or traditionally frame cameras. Frame cameras produce just images as a third and frame rate. The event cameras are capable of detecting the pixels that change, okay, and only send the coordinates of the pixel they send, the time in which the change was produced, and also if the change was positive or negative. The important thing here is that it can work at several megahertz, okay? So a typical event camera can produce several millions of events per second. So the challenge here is to process that in real time on board, and of course, taking into account the low payload capacities that these type of platforms have. Okay, so in particular, our challenge was to process that in something that is comparable in computational terms to a Raspberry Pi. And also we did that for obstacle avoidance. Here, without our system, if there's an obstacle, then the system just crash. So what we develop is a method that uses the events in order to detect the moving objects, predict their trajectory, and taking into account the kinematical constraints of the platform, being capable of deciding in real time a maneuvering to avoid that. As you can see, one advantage of the event camera is that it can work in pitch dark conditions. Okay, so it's good advantage from the visual traditional cameras. Okay, so just this is just a brief introduction to make you see, let's say, our technological capabilities. Okay, in a very brief way, and mainly related to the, let's say, to the last projects of my units. Okay, so this is the outline of the presentation, okay, which I'm going to show here, which is forest fire perception with multiple cooperating drones. The advantage of having drones is that forest fires is a very harsh environment in which there is a smoke, can be bad weather conditions, okay? There can be many occlusions, and the drones provide capabilities in order to put the sensor at the location, at vantage location, in which you can see the fire in a satisfactory way. Okay. Also, of course, by combining different drones, it's possible to extract different information from different point of views, and many techniques regarding information fusion can be applied, not only from the different types of sensors, typically infrared, and also images, traditional images, but also from the different points of view and different perspectives. This can be done in an optimal way in order to obtain, to maximize, the perception, or minimize the uncertainty in which you are seeing, monitoring the fire. Okay. This has been one topic of my unit and my research group for some years, and now we are in a project together with the University of Thessaloniki, which is the TIMA project, okay, in which we are going to extend, complement these techniques very widely, fusing a wide variety of information. I'll describe it later. So this is the outline. First, I will briefly go through the sensors and basic image processing. The basic image processing is one of the main topics in this short course. Okay, this is the responsibility in TIMA, and this is the specialty of the University of Thessalonica. I will not go very deep in this. They will go through some mathematical foundations for information tools, okay, some tools that you probably know. Then I will describe some different ways of how these sensors, this basic image processing, and these information tools can be used in order to enhance fire detection using multiple drones, UAVs, we call it unmanned aerial vehicle, okay, in a cooperative way, in such a way that the synergies from the cooperation of the drones can be exploited, okay, both from the detection and also for the monitoring. And monitoring for us is not just the gathering of images. The monitoring for us is measuring. Okay, what we really want to obtain is an estimation of the status of the fire. Status of the fire means where the fire is. Okay, how length the flame, the fire flame are. So to obtain quantitative parameters that can be useful in order to attack the fire for, let's say, for fire extinguishing, essentially. Okay. And finally, I will go to the discussions. Okay. So at the first part, I'll go rather quick, I would say, but at the final part, I will go more slowly because there are more details and more things that has to be considered. So this is, I don't know where to put it because my slides are quite full. Yes, great. So as sensors, which are the main sensors? Of course, what I'm saying here is sensors for drones, okay? I'm not speaking types of sensors, for instance, that can be installed on ground stations, okay, or can be installed in satellites, okay? I'm not speaking about that. I'm speaking from the drones. The main sensors for the drones community have been traditionally infrared and visual cameras in order for monitoring of fire. Have been infrared. The infrared cameras have the capability of detecting not the heat but the radiation, okay, of the camera, and using the physics equations, the camera can transform these quantitative radiation measurements into temperature. This can be done using thermographic cameras, okay? Of course, for using that, you have to do the calibration of the camera and input some parameters such as the emissivity of the material, secondary sources, etc., okay? But of course, you can make more relevant the objects that are hotter, okay, which is very important in fire monitoring and detection. The visual images from which it is possible to extract the fire by using some kind of segmentation. Okay, what I'm going to show here is segmentation that we developed many years ago, okay, that are essentially based on color, okay. Also, we need navigation sensors for the drones. The main navigation sensors, as you know, or you probably know, are the GPS or the GNSS, which is Global Navigation Satellite System. As you know, the GPS is just a standard, okay? It's the American standard from the American constellation of satellites. But we also have in Europe, which is Galileo EGNOS, you probably know. In Russia, they have GLONASS. In China, they have Baidu. So in total, now all globally are called Global Navigation Satellite System, which is GNSS. We have the IMU. IMU is an inertia measurement unit. It's an unit that let's say it's a device, okay, that encompasses a number of sensors such as compass, accelerometers, gyroscopes, okay. The objective is to obtain the motion, estimate of the motion, okay, of the robot. And also we have the altimeter. In many cases, the altimeter is fundamental because the GPS is very accurate when estimating the latitude and the longitude, okay, over the surface of the earth, but is not accurate when estimating the height, okay. That is how the GPS works, okay. So we need additional sensors to provide accuracy just for estimating the height. Here you can see, here you have some videos of some experiments that we have done many years ago, okay, in which you can see the infrared images. And this is a prescribed burning. This was some kind of burnings that were performed in Portugal that were coordinated by one of the world experts, most renowned and most reputed experts in the forest fire community, who is Professor Domingo Xavier Viegas, okay. He organized one of the, at that time, the most important forest fire experiments in the world, which consisted in putting into fire 13 plots, okay, with very controlled conditions. There were more than 200 firemen, okay, in the surroundings, just taking into account and preventing the fire to be out of the area. Okay, here you can see the visual image, and you can see there is a really lot of smoke, okay. Smoke essentially is the vapor, is water from the vegetation, okay, and the vegetation, of course, has water. So there's a lot of smoke, which can prevent the detection and the visualization of the images of the, let's say, of the flames, okay. And here you have the visual. This is from the same, here you have the infrared. This is for exactly the same experiment, and they say you can see that the smoke is transparent, okay, which is very, very valuable for the monitoring. Another important thing from infrared is that the infrared cameras detect radiation, okay, and not heat. What does it mean? That the parts of the fire that has higher level of radiation is the let's say is the base of the fire. Okay, the flames are the part that are hotter, but they produce less radiation. That is why in the visual, in the infrared camera, okay, you can see the base of the fire, but we cannot see very well the flames. So that means that with one sensor, you can see the flame itself with the camera, okay, with the visual camera, and with the infrared, with the infrared camera, you can detect and see and monitor and measure, okay, the base of the fire, okay. Here in this table, there are some typical cameras of different generations. Here we have one generation that in which, you know, the technology of the infrared camera has improved a lot in the last years, okay. It comes from the military sector, of course, that kind of technology, but the number of applications in the civil sector has been increased dramatically, and has pushed the costs down and the technology up. So at the beginning, there were a typical infrared camera can weigh about 8 kilos, okay, but now there are infrared cameras that weighs 100 grams, okay. It requires some cryogenic system in order to do the cooling of the sensor, which had to be just a few Kelvin of temperature, okay, about 70 Kelvin, something like that, okay. You can imagine how it's possible to reach that kind of temperature with a cryogenic sensor. But in this case, for instance, this camera can work in ambient temperature without any cooling system. So the improvement in the technology has been dramatic during the last decades or years, okay? So if we go to the, so we have these two main sensors, which are the visual camera and the infrared camera, okay, that they provide different kinds of information, the base of the fire in the case of the infrared, or the flame shape, okay, in terms of the visual. Of course, what we need now is to do some kind of processing, how to process that. The most important thing for the processing is what do I want to obtain from the processing? Okay, our objective is to do the measuring, and to do the measuring means to build some kind of model of the fire first, okay, define a number of parameters of the fire that I want to estimate, okay, and then do the suitable image processing in order to extract these parameters, okay. So this is the model that is typically standardized in the forest fire community, okay, in which you can see the width of the fire, the distance, the length, okay, and also the height, taking into account the slope inclination. And this is just using this kind of model and considering the terrain and the model in the terrain, you can build a 3D model of the flame, okay? So this is finally what we would like to obtain, a model like this, okay? And for the processing also, it is fundamental to notice that we have drones, okay? So the drones move, and they move. We need to develop some kind of methods in order to stabilize them. Of course, there are some kind of sensors in order to stabilize the images. For instance, you know, the gimbals as gyro stabilized platforms that can do it, but gimbals are typically very heavy, okay? And this is a constraint for using that on drones. So for doing that, very often what we did is to make use of image stabilization, okay? Once that you have the images have been stabilized, okay, you have to do the segmentation, okay? For doing that, you can use the artificial intelligence techniques that the University of Thessaloniki is expert of, or you can use some other, let's say, more traditional image processing techniques than the ones that we used, okay? And of course, after doing that, after doing the image processing, and you have segmented the region that corresponds to the fire in the image, you have to extract the features. What is the features? Extract, for instance, the base of the fire, the higher part of the fire, okay, of the segmented regions in the image, in order that this part can be corresponded to the model. Okay, this is also a fundamental step. And after that, we have the georeferencing. That means that what we want to build is a georeference model. It's a model that can be suitable to say the forest fire is here. This is the fire in front is evolving like this. This part is with this speed. This speed is with this speed. This is what is very interesting for the forest fire managers in order to do the management and the planning of the attack. And this requires georeferencing. Georeferencing can be obtained, of course, by using the GPS location of the drone, okay, the extrinsic calibration between the camera frame, the camera reference frame and the drone reference frame, and also taking into account the orientation that is given essentially by the data obtained by the IMU. Okay. This is some more details about the image stabilization. We have used a feature-based image stabilization, which consists in extracting some kind of features using SURF, SIF, etc. And in different images, what we do after that, we do the association. We fit that to a model. For fitting that to a model, we're assuming that the terrain in the field of view of the camera is flat. So this can be modeled by an homography, And one that we obtain the parameters of the homography. Homography essentially is a 4x4 transformation matrix that relates to planes, okay? And once that we have done it, simply we just do the image warping, which is pre-multiplying one image by the inverse of the homography that we obtain, okay? By simply doing that, okay, which is quite simple, it can be done in real time very efficiently, we can obtain results. As I said, this is the first step of the image processing for the drones, okay? Here you have some examples of the image segmentation. As I said, imagine that you have already segmented this part. Okay, if you segment this part, you can combine information from the infrared. From the infrared, you can obtain the base. Okay, the base of the fire for the infrared image, the segmented infrared images. Once that you have that, you can define the contour of the base. Okay, if you temporarily analyze after the image stabilization, you can obtain the speed of the propagation, okay? And also you can estimate which is the part that is advancing and the part that is at the rear, the let's say the part of the contour that is at the front and the part that is at the rear. This is very important as well for the modeling, okay? And also you can obtain the width, okay? And also from the features of the images, you can extract the height, the flame height. So once that you have the segmentation, the stabilization, segmentation, and extraction of features, you can obtain measurements, okay, extracted only from the processing of one kind of drone, one kind of sensor, infrared or visual images, okay? And the next thing is to combine the nodes to fuse the node, okay? To fuse the node in, let's say, in an intelligent way using different tools, okay? Here are some results that we have obtained, okay? Some videos. Here you can see this is, for instance, a static. In this case, the fire was monitored with static cameras and also with a camera on board of well, area camera. In this case, it was not a drone, but a real helicopter. These experiments were huge, one of the most important and very costly. They required a really lot of resources, and several helicopters were deployed in order to be there and to film the images in a suitable manner, okay? So in this case, two different helicopters in this were used. One is from the helicopter from which this footage was obtained, and the other one is here. You can see the other one. So here you can see this is the result of the infrared image. It is hard to see, but some of the pixels of the contour have been enhanced in order for some kind of visualization. Okay. Here you can see the processing, the segmentation of the visual image. Of course, the part of the base is colored with green, and the height plate of the flame is colored in red. As you can see here, the smoke is a real problem for the segmentation of fires, of the flames. Okay, it's a real problem. And here you can see the features extracted from the aerial image after stabilization. As you can see, the stabilization is very accurate. The error that we're taking is subpixel error, okay, which is very, very accurate. So once that you have these features, okay, you have used these sensors, you have done the stabilization, you have done the segmentation, feature extraction, okay. Now you need to combine these features, okay, in order to extract the real model, the real operation of the final system that you want to have, okay. So you need to use information fusion tools, okay? And for this, I will briefly introduce them for sure. These are tools that are known for all of you, because they are not only from the robotics community. They are applied almost in every engineering field, okay? So you have, we rely on the variation estimation. The variation estimation is optimal, or can accommodate to perception models, to sensor models, okay? The main disadvantages is that it's very computationally demanding, okay? And also you have to make some assumptions and hypotheses. And of course, it models the problem from a statistical point of view that on one hand gives you the, let's say, the tool to make it fundamentally optimal, okay, which is very, very interesting. But on the other hand, you have to assume models, okay, and also assume a statistical model, which maybe there can be some problems, okay. These techniques are very well used in many, many fields, including robotics. Okay, they are fundamental in robotics perception, part of my unit. Okay, and they're essentially based on the Bayes rule known by everyone. I will not go into details in this short course because it's very well known, and for sure have studied that in many other subjects. Okay. And yes, well, the recursive variation estimation is the implementation of this equation, which is intractable, means this equation is impossible to be computed, okay? But there are some implementations that make it possible, okay? One of the most well-known is the Kalman filter, and the other one is the probabilistic grid. Kalman filter, as you know, it has two basic steps. It has the prediction in which the system that you want to estimate is predicted, okay? Let's say the state vector of the objective of the state vector that you want to estimate is predicted considering the system dynamics, okay? And you have also the update in which all the measurements are put into the filter in order to correct the prediction. So it combines both the predictions and update in a sequential way, okay? And it can be demonstrated that the resulting estimations are optimal in case that you fulfill these assumptions, which are quite simple. In this case, that the models are linear, and then the noise is Gaussian. The noise both of the model you're considering and of the noise that you are considering are Gaussian. Okay. In case that the models that you are assuming are not linear, we have the extended Kalman filter, which is essentially, let's say, a linearization of the Kalman filter, okay, which works with the Jacobians, okay? So these equations are very easily to be computed. It's a very well-known algorithm, okay? Another tool that is very useful here is what is called the probabilistic grids. Probabilistic grids is, let's say, it's a georeferenced way or estimation way. The objective is that you divide the terrain into different cells, okay, and you assign a certain probability, let's say, value to each of these cells, okay, which can be, for instance, the presence of fire. When you have a measurement, okay, a georeference measurement, the result of an image processing, for instance, you just put that into the grid, okay? It is put as in a typical Kalman filter update, very similar to it, okay? And after the update, it does the prediction also considering in a similar way how the Kalman filter is working. Essentially, what we have here in the probabilistic grid is a small Kalman filter for each of the cells. Okay, of course, this can be computationally demanding. Okay, but it is very powerful, and there are implementations that can, let's say, solve or alleviate the capabilities required to do the processing. Okay. Oh, yes, once that we have these tools, how we can apply them for forest fire detection? Okay, so imagine that we have a number of drones, okay, and we want to detect potential fires that can occur in a certain area, okay. one thing, can be one strategy, can be each of the drones responsible of surveying a particular area, and that's all, okay? Yes, that should be nice, but this doesn't exploit the complementarity of having different drones, which is fundamental here to reduce the uncertainties. As I said, forest fires and forests are very harsh environments, in which there are a lot of uncertainty, and you have to deal it very carefully, okay, in order to estimate good validation and good estimates that are valid for forest fire attack. So another approach, the one that we developed here, and I think it's very interesting, I've been publishing several papers already, is to make use of the complementarities that we can obtain from different drones on different platforms, okay? In this case, we are using one blimp, Zeppelin, okay? And two helicopters, okay? That are endowed of different sensors. The blimp only has a visual camera that is looking downwards. The both helicopters, one have an ultraviolet fire detection sensor, and the other one, the other one has an infrared camera. So what we develop here is a strategy in which the area to be surveyed is divided into different zones. Each drone surveys its zones, and when it detects something that means some alarm that has some probability to be caused by a fire, then it calls the rest of the drones, okay? So the rest of the drones with the sensors will go there, but what does it mean where? They will be located at vantage locations, okay, that are computed in real time and determined in real time in order to minimize the error in the localization. If you have one camera like here, okay, so you can see that the error in the positioning of the drone and the orientation of the drone, okay, can cause that like a Gaussian, okay, that with an ellipsis size Gaussian just puts here. So this is the uncertainty of you have of the local of your localization. All the errors in the GPS locations, all the errors in the orientations, which can be modeled as Gaussian, when these errors are projected to the terrain, it causes one Gaussian that has this elliptical shape. Okay, and here we have the confidence area. That means the area in which 99% of the samples of the Gaussian is located. So that means that the fire can be in the middle, or can be here, can be here, can be here, in whatever place here, okay, from a statistical point of view. So the objective is to minimize this area as much as possible. Of course, it cannot be used with only one sensor. If you only have one drone and one sensor, this is what you have, okay? What you need is another one that can locate, for instance, in this way, okay, when the mouse is, in such a way that the Gaussian it produces is like that, okay? And when both Gaussians are combined, okay, the resulting value will be like this, okay? Will be much smaller. If you have a smaller uncertainty areas, it means higher accuracy, lower error in localization of the alarm, okay? So we exploited two things here. The first thing is to cooperatively control and guide the drones in order to minimize the uncertainty of the localization first. And the second one, which is even more important, is to combine the measurements from one drone and the other in order to reduce the uncertainty, not on the localization itself, but of the detection. We want to be sure that that here is a real fire. So each sensor has its pros and its advantages. So we just combined it both also in a statistical manner using the Bayes rule in order to optimize the probability of detection, okay? This is what we have from the blimp. In the case, the blimp is flying just very top. It is just producing a mosaic of the area. It is doing by extracting features and do the warping between each of the images, combining the features in a similar way as the stabilization, but in a cumulative way in order to build a full mosaic of the environment. Of course. And here we say, here in this slide, I'll go into some more details about the information fusion for the detection. So we exploit the complementarities by different drones with different sensors at different locations, okay, in order to enhance the fire probability. In this case, we are combining the probability, the detection and the false alarm probability of the different sensors from the different drones. In this case, we are assuming from a theoretical point of view, M sensors. In case that we have two, this M is just two, of course. And this is used to enhance the probability of the fire detection to be sure that it's really a fire, okay, first. And the second is to reduce the uncertainty, reduce the size of the ellipses, which is very important. If you know that there is a real fire somewhere, we really know to know where the fire is, okay? So, and this is not trivial. This is not trivial at all. If you imagine just a mountain or a hilly environment, okay, these ellipses that you have seen, in case of having a flat terrain, is simply an ellipsis. But what happens when they have a hilly environment? These ellipses can be very, very, very large. So we have to make sure that the ellipsis is as lowest as possible, as shortest, as smallest as possible. Okay, this is done, as I said, by using some theoretical developments involving the filters. In this case, what we are using is essentially both. We are combining both. For this, we're combining the estimate obtained by a common filter for the fire probability, and for this we're using probabilistic grids, okay, in such a way that here you can see, or maybe in this slide you can see better. Here you can see in black means that there is no alert, and in black that there is alert, and this is just the cells, okay, in the terrain model, okay, that correspond to is of the image. This is the image. This is the field of view of the camera after doing the projection to a terrain space. Okay, so that means that in this image there is no fire. In this image there is no fire. In this image there is no fire. In the white one there is fire. Okay. So, of course, here I'm concentrating mainly on the perception part, okay? But of course, there's a lot of information. It's impossible to be put into the short course about the control. There are also variation techniques by making use of Markov processes, decision processes modeling, can be used in order to determine the optimal guidance, okay, and the optimal locations where the drone should be in order to provide the optimal estimates for perception. Okay, this is quite a huge domain also in robotics, to determine the best actions, the best guiding in order to maximize the information from once that it's globally joined. Okay. And here you can see some results that we obtained in the experiment in terms of the file localization accuracy, okay, which is measured like a larger eigenvalue of the ellipses resulting from fusing the different measurements, okay. This is how it evolves. Here in this case, we're using this is just the ellipses, or the value of the largest eigenvalue resulting from having detected the fire using just one drone. In case that we join more, okay, if we put another drone, that value decreases dramatically. That means reduction in the error of the localization of the fire. And here you have the probability the probability of the detection. In this case, as I said, there is only one sensor, and it's one sensor. The probability that is provided just depends, of course, on the reliability assigned to the detection capabilities of that sensor, okay? When there is a second sensor, these probabilities are joined using the Bayes rule as I shown in the last slides in such a way that the detection probability increases dramatically. And as you can see, it increases more and more with the higher number of measurements that you have, okay? If you just have one measurement, yes, maybe it's a fire, maybe it's not. But if you say in one measurement, oh, it's a fire, and the next time, yes, it is a fire, yes, it is a fire, this is a fire, this information is put into the system, which each time is more and more sure that what you are seeing is real a fire. So that is why this probability is increasing here, and the false alarm probability is decreasing. Okay. So now the monitoring. Monitoring for us means measurement. Okay, what we want to obtain is to measure where the drone is. Okay, here it is the model I previously shown that we want to obtain. Okay, this is what we would like to obtain, the 3D modeling. This is the model, the main parameters. This is the skin of we are having. Potentially we can have ground stations or drone. They are essentially the same, because what we are interested in is just combining the information. Okay, so for us, joining the information from one drone for one manned vehicle or from one static camera is exactly the same. Okay, the method, all what I have said is absolutely transparent independently if it comes from a static camera or from a moving camera, a robot, a manned helicopter, is exactly the same. And if you can see here, this slide, this is quite, I like it quite much, quite a lot. I'm going to repeat the video again. This guy running, this is me. This is me in one forest fire that we made in these large experiments, okay? And the flame height was about 10 meters, something like 8-10 meters, which are huge. The heat that was produced there was amazing. And here, just an example, you can see some, this is one place of the hill, okay? It has two slides. This is one part of the hill. This is the another part of the hill, absolutely burned, okay? We were here several years, and the largest plot here was 1 hectare, okay? And one typical year, we burned about 4 hectares or 10 hectares, and we'll be there many years, okay? So at the beginning, we were working only with the static cameras, then with manned cameras, and finally with drones. Here you can see the the ground station of a drone. In this case, this is not this is manually commanded drone. This is not a robot during the fire. Okay, here you can see the result of the image camera. As you can see, it is very done, and that is the drone that we obtained. Okay, that we use. As you can see, it's very easily to detect the infrared camera, the fire in the infrared camera. And of course, what are the challenges of the measuring? Measuring is a very harsh problem, because there are many heterogeneous types of sensors. These are infrared cameras of different types, different wavelengths, okay, different kind of filters, optics, also with the cameras the same, okay. Also, this camera and these sensors are not synchronized, okay. They are produced when they are produced, okay. Also, the spatial resolution is different, because the field of view of the optical lenses of the camera they're using is different. Also, there's a very high noise level, both in the images, and also the result of the processing, the segmentation will have a huge amount of noise, because the environment is very noisy in general, okay? And in general, also, we have the computational burden. As I said, depending on the technique that we're using, it can be significantly or not, depends, okay? And yes, the challenge is harsh environments. Forest fires are very dangerous, very harsh environments. And of course, what I'm speaking here is just some, let's say, some tests. A real fire environment is a mess. It's a real dangerous, noisy, chaotic environment. Okay, so the system should have at least some robustness in order to do this. So, of course, how can we deal with the information fusion for measuring? Here I'm presenting three approaches. The first one is to know, let's say, to exploit the object that we want or the event that we want to measure and to monitor in order to perform ad hoc information fusion techniques. That means maybe we have a lateral view in which we have a segmented, we have a camera with lateral view, and we have segmented the file like this. We have a camera from the top, okay, which we have segmented like this, and we have an infrared camera in which we have segmented like this. And maybe it's possible just to extract the contour, say that the contour here should be the same contour here, should be the same contour here, the flight length here should be the same here and here. So it's possible to make use of the modeling that we want to obtain, okay, and the information that we have in order to decide which measurements and which features for each kind of image can be best combined with the others from the other images. Of course, this is one approach that we obtain, and in this case, we are not using any Bayesian estimation. This is just simple, very efficient, of course, information fusion approach. Okay. Another approach can be like using standard Kalman filters. Okay, so we have first we have for each kind of the sensor we have some kind of local single camera processing. Okay, for infrared, for visual, and also for each of the drones that we have. And once that we have that, we put them all into an extended Kalman filter that performs the multi-camera data fusion. In order to do that, we need a model to represent the fire that can be suitable for the Kalman filter. And in this case, we are assuming that we have a third time resolution, longitudinal resolution along the fire advance, okay? And in each side of this resolution, we have some parameters of the fire, such as the location, the width, the angle, and the height, okay? And so this model can we put into the standard Kalman filter. It can be predicted, okay, and it can be updated. In the update step, what we do is to assimilate, to let's say, to make the correspondence between the features that are extracted from the image processing and infrared image processing, okay, to the model. And in the prediction, what we do is to use forest fire predictions, okay, simple one, not very complex, okay, in order to do that, okay. So we experimented this approach, and this approach here, for instance, we have some results. This is the result that we obtained from this is the result from the infrared camera, frontal one. This is from the aerial image, and this is from the frontal static visual image. Here there is a lot of smoke and there's no segmentation. So each of these lines is the fire from location after georeferencing on the terrain, okay? So in this case, we can see here there is a lot of smoke. There is no measurements from the images, no the aerial images, and no the visual, the frontal visual image, but we have measurements from the infrared image here. Okay, and then by fusing them all, okay, it's possible, okay, in using the standard Kalman filter, as I said, to well, here we can see two mechanisms. For instance, in case that there are measurements of the three types of sensors, the filter essentially computes the mean between them, essentially, okay? And speaking very briefly, okay, this is more, of course, this is technically significantly more complex, okay? But I'm just speaking quickly because I don't have time. I'm running out of time. In case that we only have measurements from infrared, from the infrared image, these results dominate the estimation. So this is the final result estimation. In case that we have measurements from the theory, they are essentially the average, essentially, okay? In case that we only have from one of them, they dominate the others. So in this way, we have robustness to forest fire, to smoke, because in case of smoke, the infrared measurements dominate, okay? And here, for instance, we don't have measurements neither from the visual cameras nor from the infrared cameras. In this case, what the filter does is to the prediction. In a Kalman filter, if there is no update, the Kalman filter keeps on predicting and predicting. It provides a lot of robustness, and in this case, is also very interesting. Yes, and we have the approach 3, which is the use of probabilistic grids, which is significantly more computationally demanding, okay, but also it is much more accurate, okay, and also the accuracy can be controlled because the size of the grid can be controlled. So it provides a quasi-optimal variation estimation because it's non-linear, and when it's non-linear, the Taylor linearization makes instead of optimal, it's turned into quasi-optimal. But in any case, it is one of the best that we know. Okay, that science know. Okay, so yes, so here you can see both results, both stages in the probabilistic grid approach, which is the prediction, in which the fire model is used in order to estimate or to predict the values of the probability of each of the individual cells, and the update in which the information from the different sensors can be joined. One very important thing of this approach is that it doesn't depend, or that it works with georeference data first, because it provides a it is a georeference approach, okay? First, the second one is independent from the temporal resolution. If you have one information, you just put it there, okay? Simply put it there, and the system is capable of dealing with that, okay? It doesn't require synchronization between the sensors. Another important thing is that the spatial resolution does not mind. It's independent to that because it's a georeference approach. So that means that if we have one camera with a shorter field of view with a larger field of view, it doesn't mind. You just update the cells that for which you have measurements. And also it's very suitable. The problem is computational power, okay, but the advance in the computer made them absolutely tractable, okay. So, okay, so just to conclude, and in 5 minutes past hour, sorry, just to say that forest fire is very complex problems, very, okay? It is a tremendously harsh environment, okay? And in this case, the only way to do estimation, accurate estimation, of course, is to exploit the heterogeneity and the synergies that can be formed by different sensors, okay? Why? Because each sensor has its own advantages and constraints, and also the environment is terribly harsh and complex, okay? So that means that it requires different types of sensors, okay? And not only of sensors, but sensors at different locations. Why? Because there are many cases in which the fire can be occluded, there is smoke, there are a lot of trees, there are a lot of also the smoke is dynamic, so the forest fire influences the wind, and the wind is influenced by the forest fire. Both is there's a coupling in this here, that it means that it's very difficult to predict, okay? So in this unpredictable skin approach, and this unpredictability is even worse with the 5 and 6 generation fires, okay, which are now a problem from a scientific point of view, because there are not models, or there are very few models in order to do this prediction. And yes, and the AI is providing very good advantage in this topic. So it is very important to have different sensors, but not only that, but having the capability of putting the sensors at vantage points. Okay, vantage points and vantage orientations in such a way that we can get rid of the occlusions, etc., etc. So that requires, of course, using multiple vehicles. Of course, drones provide a solution here, but also some difficulties. Difficulties from information fusion. First, we have high temporal and spatial heterogeneity of measurements. There are tools that can be that can solve that in the information fusion community, as I said. Also, if we have a swarm of robots around the fire, of course, the communication should be reliable. Okay, this requires good communication means. I don't think it is a problem in which some years ago communication was a problem. Right now, I don't think it is a real problem. There are a lot of means communication means even satellites. This is not an actual technological problem right now. And it provides the use of decentralized information fusion techniques, which are significantly more robust. That means that each robot has its own estimate of the whole environment. Okay, this is very novel from a scientific point of view. Each of the entity has the overall view of everything and contributes by adding its local contribution. Okay. So it's very interesting, very robust, okay, but nowadays is still a challenge also, I could say, from a scientific point of view. And also the information fusion requires, of course, all the experiments that I show are very nice, very interesting, but they require vast amount of resources. There were about 400 people in the files that yes, in the experiments that I've shown. 400 people, about 200 people of firemen with a lot of equipment. Half of the equipment in Portugal were there during the time of the experiment. That is what we were told. Have all the available, I mean, in terms of personnel, more than 200 firemen were there. Okay, because and also about 200 researchers. These experiments were used not only for us, of course, but they were for a huge number of experiments: farm biology, plant recovery, wind perception. They are testing different components to add to the water in order to see their behavior, their extinguishing capabilities. It was quite amazing experiments. At that time, they were the largest experiments in the world that were performed. And I am very proud to have been to have some small part of it. And so that ends my conclusion. So sorry for being late. Okay. And if you have any questions, I will be glad to answer. Thank you very much.
Thank you very much, Mr. Ramiro. Give me a second. We're glad for having you. Let's wait for some questions in the chat.
There is one question there is something in the chat.
No, I don't think, not yet.
Okay.
Let's wait a bit, maybe. We're very glad having you. Also, everyone in the chat, if you want, you can fill some forms. There's an evaluation form in Google Forms, as well as a participation Excel. We would be glad if you could fill it. And after this, we'll have a small break.
Please send it to me. I'm sure that you have sent me. Plus, please resend them to me, okay? Because
okay. There is in the chat as well. I will send the links again.
So, I think there are no questions. So, thank you very much. Okay.
Thank you as well for having us.
And you can contact